Hello, so in this video we will talk about transformation of random variables, and specifically we will talk about the discrete case in which we have a random variable with a PMF or a probability mass function, and we want to transform it to another random variable. So let's say what we are given. We are given a discrete random variable x with a probability mass function of this, which means that we have a table, and this can be uh, you know xi, and this is p of x is equal to xi. So this kind of table we are given, and obviously this sum is 1. Okay, so and this can be infinite values but countably infinite values. That is the definition of a discrete random variable. Okay, and then we have a mapping from x to y given by some mapper g. Okay, so this g can be a proper function, it can be some other kind of mapping, and we'll see what are the situations in which we will be using our g. And what we want to find is, we want to find the PMF of y, which is probability of y is equal to y. So in other words, we want to find a table like this for y. Okay, should y be discrete or continuous? So y will be discrete. Why? Because y will be only defined by this xi. So for example, we have g x is equal to xi's. If xi's are finite or countably infinite, then g of x at xi should also be countably infinite or just finite. So this means that since this is g of x is y, so then this means that y, the number of values which y can take can also be just finite or countably infinite. Okay, so this is for the introduction. So let's start with how we proceed to find the PMF. So let's say this blue thing is my g of x. Okay, this is my x and this is my y. Now these red lines are the values where x is defined. So this is x1, x2, x3, x4, x5 and x6. Okay, and then we have a table for our each of these x1, x2, x3. So these are the probabilities, and you can check that these add up to 1. Okay, now let's say this is my y1. Why do I check the intersection of this and this? Because these will be the only values at which y will be defined. Why? Because x is only defined at these vertical lines, and we have to find the corresponding values of y. So we will find the intersection point like this. So we'll say this is my y2, this is my y3, this is my y3. Okay, similarly this is my y4, this is my y5, and this is my y6. Okay, so this means that whenever we have x1, we can find our x1 is mapped to which one? Our x1 is mapped to y1. So we'll say this means probability of x is equal to x1. This is equal to probability of y is equal to y1. And similarly, x2 is mapped to y2, x3 is mapped to y3, and so on. So we can just say that probability of x is equal to xi, this is equal to probability of y is equal to yi for I, this is equal to 1 to 6. This is one case in which we just find the PMF of y by just simple mapping of gx and the values at which x is defined. Okay, so now let's consider another case. So now let's consider that we have a case like this. We have, this is x1, x2, x3, x4, x5, x6 here, and x7 here. Okay, now again we have a mapping this to this, this to this to this guy here. So this is, my drawing is a little bit off. This guy here. So we should actually write like this, draw like this. So here, here, and then this guy and this guy are mapping to the same point. And then this guy is again here. Okay. So in this case, we have, this is my y1, this is my y2, this is my y3, this is my y4, and this is my y5, and this is my y6. So now note that we have 7 values for x but only 6 values for y. So again, for p of y is equal to y1 is just p of x is equal to x1, and we have for y2 the same, but for y3 we have 2 values of x which map to y3. So then we just add them. We say p of x is equal to x3 plus p of x is equal to x6. Okay, and so we have this, then we have this, and then we will say y is equal to y2, this is p of x is equal to x2, and we have the last one, y is equal to y6, this is equal to probability of x is equal to x7. Okay, so then this will be my PMF. Now what did we learn from the previous two examples? We learned that if y is equal to g of x is a unique mapping. By unique, what do we mean? One-to-one mapping. Then we'll use p of y is equal to y. This is the probability of g of x is equal to y, which is equal to probability of x is equal to g inverse of y. So this g inverse exists. Why? Because this is one-to-one. Okay, so this is my first case. Okay, what is my second case? My second case is if g of x is not one-to-one. Then for each point, so for then we add them. So we'll say probability of g of x is equal to y is equal to summation of I is equal to, let's say, 1 to k. Probability of x is equal to xi is equal to g inverse of y, where g of xi's, they're all equal to y for I is equal to 1 to k. So what does it mean is that this, in exactly in this situation, we have k is equal to 2 here, where 2 of the x values map to one y value. Okay. So in this case, we'll just add them. We just say, we just find the value, number of values for which we have one y value for a number of x's, and then we add them, add the probabilities. Okay. So let's do an example to illustrate this. So let's say we have x, this is a geometric random variable with parameter p. So what is the support of x? So x is in 1, 2, 3, they are all natural numbers here. And what is the probability of x is equal to x? This is equal to 1 minus p to the x minus 1 times p. And let's say we have y is equal to u of x minus 3. So what does u of x minus 3 means? That this means y is equal to 0 if x is less than 3 and y is equal to 1 if x is greater than or equal to 3. Okay, so this is what it means, that we have a function like this. So let's draw this. So we have this guy, so then this and this. So this is my 3 here. So this is my x, this is my y, and this is a 1. Okay, so now x is defined at this point. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and so on. Okay, so this means, based on our discussion before, we will have one-to-one situation or many-to-one situation. We have many-to-one situation here. So first of all, since y can take only two values, so we can only have to find probability y is equal to 0 and probability y is equal to 1, right? So this is equal to what? We have 1 and 2. So there are only two values for which probability of y will be equal to 0, because only two values of x map to y is equal to 0 here. Okay, so then this is equal to probability of x is equal to 1 plus probability of x is equal to 2. This is equal to 1 minus p to the 0 times p plus 1 minus p to the 1 times p. Okay, so this is equal to p 2 minus p. Okay, and this is equal to, just because these are probabilities, so actually you can use this situation, x is equal to 3 plus probability x is equal to 4 plus so on, and use the geometric mean formula to do that. But there's an easier way, so we can just say 1 minus p of y is equal to 0, which is equal to 1 minus p 2 minus p. Okay, so this will be our probability mass function for y, given we have this mapping for y is equal to x and we have x as a geometric random variable. Okay, so now as a summary, what we have done is we have formulated a way to find the PMF of y when the PMF of x is given and a mapping from x to y is given. Okay, so what we did was we split our situation into two cases in which we have g of x is 1 to 1 and when g of x is many to 1. And then we said how can we calculate the PMF of y in both these cases. And then we illustrated this by an example. So hope it was easy to understand, and thanks for watching. Hope you liked the video.